let me introduce Professor Mike Brown.
So it's a funny thing about that asteroid. I forget about that asteroid sometimes, but the thing about that asteroid that I've noticed, I had to look it up when it was named after me. It's pretty eccentric, and it's not very bright. So I don't know why they chose that. So the title that you thought you were coming to tonight, I think, was this one. You saw it, but since I developed this talk and since I wrote the book of the same name, there have actually been some significant new developments that have led me to have to change this talk. You'll see where the talk has changed. But one of the important changes is I had to change the title. It's a really sort of very different title. The new title is this one. And you'll see near the end, if I forget, somebody will have to remind me. But near the end, you'll see the big changes that have happened just in the last year, and we'll get to that. But the story of why Pluto was dead, or why Pluto got killed, and why it had it coming, really started with the very earliest explorations of the outer solar system and the search for something in the outer solar system itself. Early on in the last century, astronomers were convinced that there had to be another planet out there somewhere beyond Neptune. Neptune had just been discovered, and it had been discovered because it was tugging Uranus ever so slightly in Uranus's orbit, so Uranus wasn't quite going as fast as it should have been. And astronomers watched Neptune and realized it too looked like it wasn't going quite as fast as it should have been, and maybe that meant there was another really large planet out here. We know now, actually, that those data were just in error. Neptune is actually doing exactly what it should have been. There is nothing out there pulling Neptune along. But astronomers at the time really thought there was something there. And so they did the smart thing, calculated where it should be, went to a telescope, took a picture of the sky looking for this new planet, and there it is. Do you guys see it? You don't see it. So they didn't actually see it either. So they went back to the drawing board, worked out the theories, looked again, and couldn't find it. Eventually, as many of you know the story, Percival Lowell founded the Lowell Observatory in Flagstaff. One of the goals of the observatory was to look for what he called Planet X. And of course, they hired Clyde Tombaugh off of the farm in Illinois to come and look for this planet. And Clyde Tombaugh was smart enough to realize that he didn't actually know what a planet looked like. So instead of just taking a picture like this, he took a picture like this, and then the next day he took another picture like that, there it is, and he watched it move. Did you guys see it move? Yeah, sure he did. Okay, so the nice thing about planets, instead of all these stars and galaxies, the stars and the galaxies in the sky are in the same place night after night after night, but anything that's going around the sun in the solar system moves. And by that motion, it stands out very easily. You can find these things by that motion. So let's do this again. These are actually the pictures that Clyde Tombaugh took in 1930, the discovery of Pluto. Let's see if you can find it. Here's the first night, and here is the second night. Anybody see it? You sure? Liars. Let's try it again. First night. Second night. Anybody see it? Okay, I don't know why, but something about the physiology of the human brain-eye connection. If you repeat something 4 times, people always find it. I don't know why. But so here it is again, the first night. Here it is, the second night. There it is. So, all right, how many of you guys who thought you saw it really saw the right thing? Anybody? Anybody? There we go. We have one. Okay. So this is it. These are actually the discovery images of Pluto. There it is without the arrows. It's a little harder, but you can still see it now. There it is without the arrows, right there, that little dot. And when Clyde Tombaugh found this little dot, he knew he was looking for a massive planet in the outer solar system because it was perturbing Neptune, even though that wasn't true. But that's what he thought. So he was surprised when he found something so small and faint. He really expected to find something sort of this big, which would have been a Uranus or a Neptune-sized planet. Instead, it was this tiny, tiny little thing. I like to think that back in 1930, it was a lot more fun to be an astronomer than it is today. Today, we make discoveries and we write these scientific papers, and they actually kind of have to make sense, at least a little bit. back in 1930, you could actually make stuff up that was crazy. And so Clyde Tombaugh didn't do this to his credit, but some other astronomers had to come. People wanted to explain why this little blip of light, which looks so small, was actually so massive. And so my favorite of all the explanations that I saw were that it looks so massive because it's so small, but it's so massive because it's made out of a core of solid uranium. Okay, so this is 1930. They didn't know yet. That's a really bad idea. Core of solid uranium, which is then covered by a liquid oxygen ocean. So the liquid oxygen is clear, which is nice, and it also actually acts as a little lens that makes the core look even smaller. So when you see Pluto, all you're seeing is that tiny little core, and the actual planet is much bigger. So as Taft mentioned, New Horizons is going to be there in a couple years. I don't think this is what they're actually going to find. These days, we actually know there's a much better reason that Pluto looks so small. Anybody know what it is? Oh, yeah, it's because it's really small. Yeah. So even in the whole debate about whether Pluto should be a planet or not, everybody knows the answer. Pluto shouldn't be a planet because it's small. But even people who sort of accept that, I don't think most people really have a very good concept of how small Pluto is compared to the other things in the solar system. So I'm going to show you this picture over and over again tonight to give you this context. And so I'm going to walk you through it here for a minute. First, these are the planets. These are the large objects in the solar system, all at their actual size. You almost never see pictures like this of things at their actual size. Usually you see things like lunch boxes that have planets that are all more or less the same size, Jupiter a little bigger, things a little smaller. These are the real sizes. The reason you don't see things at the real sizes is, of course, it's hard to put them all in one figure like this. And what you can't do is put them at their real distances. If you put them at their real distances and the real sizes, you would mostly have a big blank screen. But if you at least cram them down into one screen here, you can see their real sizes. So here they are. Here's Mercury, Venus, Earth, and Mars. The huge Jupiter in the background, too big even for the screen. Saturn, even without its rings, is quite a massive place, big place. Uranus and Neptune. And you can also see between Mars and Jupiter, you see these little dots. These are the asteroids that were discovered a couple of hundred years ago. And these are about their real sizes. They're Ceres. Ceres is the biggest one. It's the only one that's big enough to be more than one PowerPoint pixel across on the side. So you can tell there it is. And there are about a dozen that are big enough to be one PowerPoint pixel. And there are millions of other asteroids, including that one named Mike Brown somewhere out there in this region here. Pluto, you ready for Pluto? Anybody guess how big it is? So I want you to think in your mind how big Pluto really is. And then here it's going to come. You ready? Everybody ready? Okay, there it is. It's really small. I mean, this was, I think, lost in this debate, that this thing is really, really quite tiny. It's something like 2/3 the size of our own moon. I mean, it's a really, really small thing out there. And if you look at it compared to the rest of the solar system, and you don't think that it's made out of uranium with the liquid oxygen ocean, you look at it and you think, that doesn't fit. Something funny is going on, it doesn't fit. So not only is it a little bit funny in how small it is compared to the planets here, the other thing that was immediately noticed is how strange the orbit is around the sun. Here I'm going to now show you the distances of the planets and how they go around the sun, and not their real sizes. I'm only going to show you Jupiter, Saturn, Uranus, and Neptune. All the other guys are tucked inside here tightly. You can almost not even see. If I put Pluto onto this slide, it looks like this. Pluto, as many of you know, it kisses the orbit of Neptune right here, goes a little bit inside, comes around the outside much further away. It's a very elliptical orbit. And what's more, if I took this screen and turned it on its side, you would see that Pluto's orbit was tilted by about 20 degrees compared to the very flat disk that all the other planets are in. It's a very, very strange-looking thing. If you discover this in 1930 and you don't know of anything else out there, it just doesn't fit. So what do you call it back in 1930? Well, in 1930, first off, they still thought it was bigger back then, so that led them in one direction. But there was just nothing else out there in the outer solar system. They were planets New planets had been being discovered. They were all progressively further from the next one. Something further than Neptune was discovered. Very naturally, everybody called it a planet. I think that was the obvious thing to do. I think I would have called it a planet back in 1930 if I haven't known any better. Since 1930, though, something fairly extraordinary has happened. It didn't happen for a while. It didn't happen for 62 years after the discovery of Pluto, but 62 years after that discovery, the first new object beyond Pluto was discovered. In fact, discovered right here on top of Mauna Kea with the 88-inch telescope at the University of Hawaii. Since that one discovery in 1992, as of today, there are something like 1,200 objects known in the solar system beyond Neptune. And if I put all those objects on the slide, they look sort of like this. They fill up all the space beyond Neptune. Not only do they fill up the space beyond here, but in fact, some of them are even in between the giant planets. All of these objects, can you guys see this at all, this red dot? What if I move it really fast? What if I go like this? Okay, so you can't see it. I'll try not to move very fast. These objects, all these objects in this region outside of Neptune are what we now call the Kuiper Belt, after a Dutch astronomer who sort of vaguely predicted kind of its existence back in 1950. He really didn't at all predict its existence, but everybody kind of liked him, so they named it after him. So this is the Kuiper Belt, and these objects that are inside of Neptune used to be part of this big swath of the Kuiper Belt, but at some point they got a little bit too close to Neptune. And when you get a little bit too close to Neptune, it's the inverse of what happens when we have a spacecraft that we're trying to send to the outer solar system. In fact, the New Horizons spacecraft to Pluto did the same thing. We always send that spacecraft out by Jupiter, and it gets a slingshot past Jupiter to get going really fast and spun around. Same thing can happen the other way. This guy gets too close to Neptune, it gets slungshot, is that a word? Slungshot in to the inner solar system. And so these guys used to be Kuiper Belt objects. They're on their way in here to eventually become things like comets that we'll see in our own sky. Pluto, anybody see Pluto? Where's Pluto? There's Pluto. That little blue dot right there is Pluto. If you put Pluto's orbit in here, Pluto's orbit does a really nice job of defining both the inner part and the outer part of this Kuiper Belt. And in fact, if you put all of the other objects and the orbits of all the other objects on there, they would all be kind of like Pluto. They would be elongated, tilted in different directions all over the place. Suddenly, Pluto has a family. It's very obvious when you look at this that Pluto belongs to this population. So there was a time 6 or 7 years ago when officially Pluto was still a planet, but we knew all of this already. And so people sort of got around this by saying, Pluto's a planet, sure, but it's clearly part of the Kuiper Belt. It's a Kuiper Belt object and a planet. If you really, really, really wanted Pluto to still be a planet, and I know some of you did, I'm sure you're out there somewhere. Back in we're going to go back almost about 10 years now. If you go back about 10 years, these things we had known about the Kuiper Belt for going on 10 years. Pluto's status was looking a little bit dubious at that point, but it did have one claim to fame. Its one claim to fame was, if you looked at this plot again, there's Pluto again. I'm going to put the sizes of all those other objects that were discovered, and they were small compared to Pluto. There were a couple that were getting bigger as time went on. You could see them, some bigger ones, but that one's about a third the size of Pluto. Most of them are more like a tenth the size of Pluto, or even much, much smaller than Pluto. So the excuse for keeping Pluto a planet back then was, yes, it's part of the Kuiper Belt, but it's the only really big thing in the Kuiper Belt. The problem with saying it was the only really big thing in the Kuiper Belt is that actually most of the Kuiper Belt had never really been looked at. Most of the solar system had never been searched for these things like Pluto. Clyde Tombaugh had done a very good job of searching the whole sky looking for Pluto, but he could only have found the brightest one object that was out there. Astronomers, since Clyde Tombaugh, had done something very different. I'm going to forget which slide I had. This is the blank slide where I'm supposed to tell you the story. That's the slide. The astronomers had done something very different, which is they had used these new modern digital cameras, CCDs, which were fantastic. It's the stuff that Keck has. Every instrument has one of these nice digital cameras on it. But for many years, these digital cameras were really, really tiny. and you could only look at a tiny swath of the sky. So astronomers could look at any tiny swath of the sky they wanted to, probably find a tiny little Kuiper Belt object, but they may well have missed a really big one here, or here, or here, or here. The trick to fixing this was the very first of what's now a fairly routine thing in astronomy, which are these very wide field digital cameras designed to look at huge swaths of the sky at once. And the very first one of these wide field cameras we made here down at the Palomar Observatory. The Palomar Observatory is kind of my home observatory when I'm not here at Keck. It's in just east of San Diego in the mountains there. And it had, for many years, before Keck came along, it had the biggest telescope in the world at the Hale telescope. And this is not that. This is the much, much smaller 48-inch telescope that sits beside the 200-inch telescope, the Hale telescope. And they built the 48-inch telescope back at the same time as the 200-inch telescope because they had money left over after they finished the 200-inch telescope. I don't... Taft, does that ever happen these days? I'm not sure. They had enough money left over to build another telescope, but that is a little bit ridiculous. But so they built this telescope to cover big areas of the sky to find things for the 200-inch telescope to look at. Of course, it used, at the time, in 1950, it used photographic plates like everybody else did. Those photographic plates were the same sorts of things that Clyde Tombaugh used to find Pluto. They're great for looking at wide areas of the sky. They're just not very sensitive. So nothing other than Pluto had been discovered till then. Starting in 1992, all of these new objects that were discovered, most of the early ones here at Mauna Kea, were found with these digital cameras. We finally got this really huge digital camera at Palomar Observatory that we put together, and this is 2001 where we got it. In 2001, it's hard to remember back, 10 years ago. Everybody think back about the digital camera that you had 10 years ago. You didn't have it on your phone. You didn't have the little backup video for your car that said, don't hit the trash can. You might have had like a little 400 by 600 camera if you were really fancy way back then. So back then, this was really impressive. We had a 180 megapixel camera. It still sounds pretty good. At the time, it was the biggest astronomical camera in the world. These days, it's not. These days, it actually doesn't exist anymore. But at the time, it was really impressive. It covered, anybody want to guess how much of the sky it covered? Think about an impressive amount of sky. It covered this much sky all at once. That was incredible. This much sky at once meant that you could actually do something. What it meant you could do is one night you could do this, 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 and this. Next night you could do this, 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 and this. Start back up again. And in a reasonable amount of time, where reasonable is defined as about 9 years, you can cover the entire sky. And that's what we needed. We needed a moderately big telescope that we could use night after night after night, cover the whole sky, and see what was out there. I was convinced at the time, back in 2001, that the only reason that Pluto seemed special was because nobody had looked for these other big ones. And in fact, I made a bet with a friend of mine in 1999, December of 1999. It's actually the opening scene of this book. It's in December of 1999. I'm sitting up at the 200-inch telescope at Palomar, and she asked me what projects I'm working on, what I'm interested in, and I make a bet with her right then that in 5 years, somebody is going to find something bigger than Pluto. And I was convinced somebody was going to do it, and I was convinced it was going to be me because I was working on this project here. I'm going to forget to tell you how this bet turns out. So if I forget to tell you, ask me at the end of the questions how it turns out, because it's a little bit of a twist. But it's December of 1999, and it's 5 years. So I'll let you maybe do the math. Okay, so here's the telescope. Here's the project. I want to show you what we did night after night after night after night. We got data that looks sort of like this. A huge swath of the sky. And if you take your huge swath of the sky and you look at a tiny, tiny, tiny little postage stamp on it, you get something that looks like this. Something that looks like this. It was all robotic. The data would come to my office in the morning. I would sleep at night for those 9 years. It was a fabulous thing. My wife still talks to me. That's also a fabulous thing. I would sleep. I would get the data in the morning, and the computer would process most of the data, and the computer would look at a picture like this and say, well, that's a star. It doesn't move. That's pretty boring. Throw it away. That's probably a galaxy. Even more boring. Throw it away. Stars, 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 stars. Hey, what's that? And the computer would do like any of us would do, like, hey, and make a big flag and say, look at this. So every morning I would come in for about half an hour and look at things that the computer had flagged as potentially interesting objects. I'm going to only show you the real ones, but there were a lot of things that the computer will sometimes get fooled by. Like you can see even on this screen, see that little dot that appears right here? It's just a little glitch in the camera, and there are glitches all the time. Every once in a while, you'll accidentally get 3 that line up in a row like this, and so the computer's fooled. Your eye is really good at knowing what's real and not, though. So you see this, and that's something that's real. It's moving out there. The really nice thing about this project is just from looking at that image, that's 3 pictures taken over the course of 3 hours, I can tell you a lot about that object. That object is an object that is, I have to go look at it first. It's at the outer edge of the Kuiper Belt. And it's about a fifth the size of Pluto. And I can tell you that because of 2 things. One, I can tell you that it's at the outer edge of the Kuiper Belt because of how fast or how slow it's moving. The further away something is, the slower it moves. The closer it is, the faster it moves. Mostly we're looking for things that are really quite far away, so they're moving very slowly. This is actually very slow. This is the speed, if you pluck a hair out of your head and hold it about arm's length, it's the width of a hair in about 24 hours. So that's how much that thing's really moving, not very much at all. But there are things, we see a lot of things that move faster in the solar system. Anybody want to guess the fastest moving thing we ever see when we look at these pictures? Comets? Comets? No, come on. That's closer than comets. Space shuttle is really fast, but we see things a lot faster than the space shuttle. Asteroids are slower because they're further away. They're actually out beyond Mars. So the space shuttle has not yet gotten out. Shooting stars are good. You're getting closer because they're in the atmosphere. Mercury, Mercury would have to look really too close to the sun. We get in trouble. Satellites, moon, shooting stars. There's one that's even closer than all those. Airplanes, thank you. Airplanes. The problem with airplanes is they're also kind of big. They look like this. So Palomar, when it was built, seemed like a really nice spot. Turns out to be in the landing pattern of the San Diego airport these days. So, all right, okay. So the airplanes, we'll toss those out. But everything else that you guys said, except for Mercury, that we never looked at the sun so closely. Everything else that you guys said, we saw at some point and saw it moving. And we would see shooting stars. They would move so fast that they would be a streak across there. We would see asteroids. We would see moons of Jupiter. We would see all these things moving, and as you moved out to the beyond the solar, moved out through the solar system, they would be moving slower and slower and slower until finally you got to the Kuiper Belt, where these things were moving very, very, very slowly. So that's how I know how far away it is, by looking at its speed. I can also tell you how big it is, sort of, by seeing how bright it is. So there are 2 things I know. This one is kind of far away because it's at the edge of the Kuiper Belt, and it's not very bright. This is one of the fainter things that we ever see. The bigger you are, of course, the brighter you are. But the further away you are, the fainter you are. So you sort of have to do those 2 in your head and look at this and say, okay, that thing is about a fifth the size of Pluto, and calibrate your brain that way. I'm going to give you a couple more to help calibrate you. Okay, so watch how fast that one's going, and I want you to tell me this next one. First off, what about the speed? Is it faster or slower or the same? Yeah, I'd call it the same. So it's also near the outer edge of the Kuiper Belt. And how about how bright it is? This one's a good bit brighter. This one is actually, instead of being about a fifth the size of Pluto, this one is about a third the size of Pluto. It's in the top 20 of the largest Kuiper Belt objects known these days. It's not anything that anybody would have read about on the front page of their newspaper, but it was still, I have to say that, you walk into your office in the morning, you sit down, and these things start to flash on your screen, and every time you find one of these new ones, which in the prime time we were finding them maybe once a day, once every other day, it's just an incredible charge. This is a ice ball that's a fifth of the size of Pluto floating through the outer solar system that no human has ever seen before. And to that moment, you see it flashing on your screen. And it is just a great feeling to see these things. It's really exciting. Okay, let's do the next one. What about that? Faster or slower? I'd say it's a tad slower, I would say. So it's a little bit further away. It's the very outer edge of the Kuiper Belt. And how about brightness? It's a little less bright, but it's a little further, so it turns out to be about the same size, third the size of Pluto. Anybody else see anything interesting there? Yeah, how about this one? It goes from here to there. What do you think it is? Planet? Planet? Well, we'll have to talk later. Anybody guess? Main belt asteroid. All three words. That's good. It's an asteroid. Remember, those asteroids are those things between Mars and Jupiter, and they are much closer to us, and they're also moving much faster. This thing is it's fainter than this one, but not much fainter than this one. This one, as I said, is about a third the size of Pluto, which puts it at something like 800 kilometers across. This thing is about the same brightness, but it's a lot closer. It turns out to only be about 10 kilometers across. It's a tiny little insignificant thing. The only reason you would ever read about this one is if it were heading straight toward us and killed us or something. We'll never know because no one ever tracked this down after we found it. So when it comes around and hits us and we go back and look at the old data and say, oh yeah, we took a picture of that back in, then I'll be really embarrassed. Okay, so I've put you through all these to sort of put you in the frame of mind that I was in January of 2005. January of 2005, I went into my office like I did most mornings. Oh, I heard that. I went into my office like I did most mornings. I was looking at the data from the night before, and I was flipping through some, and I came on this one. And I nearly fell out of my chair. And I nearly fell out of my chair. One is because I slouch way too much. I need to stop doing that. But two, I mean, what are the other two obvious reasons? It's slow and it's bright. It's the slowest object we had ever seen. Slowest object we'd ever seen immediately means most distant object we'd ever seen. That's cool to begin with, because if you remember that last object I showed you, I told you it was at the edge of the Kuiper Belt. This one is slower than that. That's kind of cool. But this is the brightest object we had ever detected in our survey. That's also cool because bright objects are big and they're easy to study and you can do all kinds of good things with them. But if you put the two together, if it's that far away, it shouldn't be bright. If it's that bright, it shouldn't be that far away. You put the two together, and in technical terms, it means it's really, 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 really big. So we knew right at this very moment of seeing this. It took me a grand total of, I think, literally 30 seconds of staring at this picture at first and picking myself off of falling out of the chair and doing a quick calculation on my desk and saying, this thing is bigger than Pluto. This thing has to be bigger than Pluto. Not only is it bigger than Pluto, but it actually might be really huge. We didn't actually know how big it was. We only knew the lower limit. And the reason, all this time I've been sort of telling you that I know the sizes of these things, but I've been kind of lying to you. We're just sort of estimating the sizes. The reason we don't really know the sizes is because all of these things that we see out there, all we see from them is reflected sunlight. And it's bright, and that means there's a lot of reflected sunlight coming back to you. But you can have a lot of reflected sunlight in two different ways. You can have a compact object with a really bright surface, like a snowy surface, and that reflects a lot of sunlight. Or it can be a lot bigger and have a dirt surface, and the dirt doesn't reflect as much sunlight, but it's a big object, so there's a lot of sunlight coming back to you. So either one of those, to us, looks exactly the same. But we were excited because we knew, even if it had the brightest material on the surface that we could imagine, fresh snow on the surface, even then, it was the size of Pluto or bigger. If it had dirt on the surface, it was the size of Mars. This very first email I sent to the two collaborators who I was working with on this, who are Chad Trujillo. Chad's not here, is he? Chad works at the Gemini Observatory these days and just lives across in Hilo. And David Rabinowitz, who's at Yale University. I sent an email to those two guys as soon as I saw this thing, and I said, okay, here's the discovery, and it's, if it's got snow on the surface, it's bigger than Pluto. If it's got this on the surface, it's the size of Mercury. If it's got dirt on the surface, it's the size of Mars. And we were as excited as could be to try to figure out exactly what was going on this object here. Of course, we wanted to know how big it was, but we also knew that there was another good way to figure out, is this thing a big, massive, Mars-sized, planet-sized object, or is it really just one of these kind of smaller Kuiper Belt objects masquerading as something interesting? One way to at least get a clue about that is to figure out what kind of orbit it has around the sun. As you noticed earlier, the planets, the big, massive, dominant planets, all have very nice circular orbits in one disk around the sun. Nothing else does. So, question one, what kind of orbit does it have? Well, it's a little bit hard to answer that question because right here you're looking at 3 hours out of what turns out to be a 580-year period around the sun. We didn't know that at the time, but that's what its period around the sun is, 580 years. 3 hours, 580 years. It's really kind of hard to extrapolate the rest of the part around the sky. And you don't need all 580 years to figure out the orbit. We haven't actually seen all of Pluto's orbit around the sun, but we know very precisely where Pluto's going to go. But you do need, roughly you need about 5 or 10% of the orbit to get a very good estimate of what sort of orbit it has around there. 5 or 10%, 580 years, that's, 50 or 20 or 50 years, something like that. So, as I said, this was 2005, so I'll be coming back to you in 2055 to tell you what the orbit of this thing is. But that would be a little tedious. So instead, we did this very clever trick I like to think of, which is that astronomers have perfected nicely, which is astronomers can go backwards in time. And you guys can't. I'm sorry about that. But it's a pretty cool trick. So here's what you do. This object is not a particularly faint object. The only reason no one has noticed it before is because no one was looking for things that were moving. Many, many people in the past have taken pictures of it and not known it. And we went through archives of old pictures in the approximate area that we thought it was supposed to be and picked out all these spots where there was a bright star that's not supposed to be there, because we would compare other pictures and we'd say, this could be some boring gamma ray burst, but it might be actually this object that we're looking for. So we would try to create an orbit with that, and then we'd go back to some other pictures and say, hey, there's an object right there. It might just be some crummy supernova, but it might be the object that we actually care about. And we would make up the orbit there and put it there, and we'd go back. And finally, we traced it back. The earliest picture we ever found of this object was from 1954. And my favorite part of the story was 1954, and the picture was taken at the same telescope that we discovered it at 50 years later. It was one of the big photographic surveys that was being done for the 200-inch telescope then. Okay, so we've got 50 years worth of data. We know exactly where this object is. What's the orbit? The orbit, well, first off, I told you it was far away. How far away is it really? It is way out there. It's really far out there. I mean, if you were going to have another planet, that would not be a bad place to put it, right? You sort of see how they're... I mean that almost seriously. Well, almost seriously. You sort of see the arrangement of the planets, and there's sort of an order, and you would like to have one kind of here. It would be pleasing aesthetically to have one there. This is not a bad spot. So, what does the orbit look like? Well, the orbit looks a lot like this. Here's the very, very crazy eccentric Pluto, Jupiter, Saturn, Uranus, Neptune, crazy eccentric Pluto. And in green here is this object, even more eccentric than Pluto. It out-Plutos Pluto. It out-Plutos Pluto on eccentricity. It also out-Plutos Pluto on the tilt. Remember how I told you Pluto had that crazy 20-degree tilt compared to the other things? I'm going to show you this one. This guy is tilted by 45 degrees to the planets. 45 degrees. Most of the time when we talk about these objects that are out there that have these crazy orbits, elongated and tilted, usually we blame Neptune. Neptune is sort of the bully of this region of the solar system, and things get close to Neptune and get flung around. And this one, it's hard to blame Neptune for. It's tilted by so much that no one has been able to figure out a way that Neptune can even do this. So this is actually... even 6 years later, it remains a complete mystery why it has such a tilted orbit. I still blame Neptune, and I just think it did something when no one was looking. I don't know what it was. But we really don't know exactly what happened. Okay, so it has a crazy tilted orbit. That should already be your first clue. It's not going to be one of these big, massive things. It's probably not going to be as big as Mars. So we downgraded our expectations, but we very quickly got pictures with our very favorite telescope that's not on the ground. Our very favorite telescope not on the ground is this one, the Hubble Space Telescope. Usually you have to wait a year or longer to get them to look at something that you're interested in. You put in a proposal, astronomers review it, you wait, you forget that you did it, you go do something else. Eventually the data come in. In this case, there is a nice mechanism where you can just very quickly get some data for something very exciting. We called up the director and we said, hey, we just found something bigger than Pluto. Could we take a look at it? He was like, yeah. So very quickly, we turned around, we got the picture of this telescope of this new object, and it is, I have to tell you how excited I was at this moment in time, because I'm going to show you this picture. This is going to be the best picture of this largest thing that we know of in the outer solar system that you'll probably see in your lifetimes. And I knew this was coming down, and I knew it would arrive into my computer at like 2 in the morning in one August morning. And I went down to my office, drove in, waiting for it to happen, downloaded it as soon as it came up, put it up on my screen, and there it is. Doesn't that just make you want to cry, actually? So I did what I always do, which is to think, oh, no, I did something wrong. And I double-checked that we were really looking in the right place. We really were looking in the right place. This really is it. And, in fact, it's not even as big as it looks. With a very careful analysis, what we did is we had here, this object is here. Right here, you can't see off the side of the screen. There was a star, and we carefully went back and forth between this and the star 30 times to really carefully calibrate exactly what we were looking at. And after that careful calibration, we realized that it's really only that big. Even the rest of this is not actually there. Really only that big. If it had been Mars, it would have been sort of like this. Mercury, it would have been sort of like this. Pluto, it would have been sort of like this, maybe. So this size is 2,400 kilometers with an uncertainty of about 100 kilometers. Or in the units that anyone cares about, that is 5% bigger than Pluto with an uncertainty of about 5% or so. Which, you tell that to the press and they say, bigger than Pluto! So bigger than Pluto it was. Very exciting. Find this thing bigger than Pluto. But in reality, even at the discovery, when we found the size, we would say to people, hey, really don't think of this as like this thing is this massive planet bigger than Pluto. It is essentially a Pluto twin. We got some very nice data looking at the surface of it here from Keck as soon as we discovered it and found on the surface it looks like Pluto. It really is, we thought at the time, just a second Pluto, slightly chubbier, but essentially the same thing. Not the big change in the solar system that we thought it would. So I'm going to put it in context. Here's your favorite picture again. Notice that I filled in some more. Most of these other ones that I filled in were ones that we discovered over that period of time. Here's my favorite. This one's crazy, elongated, spinning every 4 hours. And there's Pluto again, and I'm going to put in this new discovery. Watch very carefully. There it is. Okay, now I'm going to take it away. Now it's gone. Here it's back. Gone. Back. Somebody up there is having to do these flipping the slides for the webcast. Sorry, webcast, you have no chance of being right. Now it's gone. Now it's there. Now it's gone. Now it's there. I have really bad news for all of you, many of you who braved the Waimea storms to come out here tonight. Look at this. Oops, don't look at that. Look at this. This discovery really means absolutely nothing. I'm serious about that. In the grand scheme of the solar system, this discovery means nothing. This solar system and this solar system are exactly the same solar system. There's a little bit of change in what's, this minor population of things in the Kuiper Belt. But really, it's the same solar system. This discovery means nothing at all. And that really should have been where it was probably left back in 2005 when it was discovered. But the problem is, at the same time that this discovery changes nothing, it has the unfortunate side effect of also changing everything. And by that it means it changes the question that everybody had to answer. Before, at this stage, the question you have to answer is, okay, we know these things are all Kuiper Belt objects, but what about this thing? It's the biggest one. It's not the biggest one by a lot these days, but it's the biggest one. Is it a planet or is it not a planet? And you know what you could answer? At that point, back in 2005, you could still answer, yeah, I don't care. We'll just leave it. You know, Pluto's a planet, it's been a planet, who cares? Leave it. We don't care. Go away. Leave me alone. And that's kind of the attitude that astronomers had in 2005 until it all got mucked up with just this one addition, because that's not the question anymore. What's the question now? The question is, all right, so what's that? Is it a planet? It's bigger than Pluto. Is it a planet? Kind of doesn't make sense, but then kind of Pluto doesn't make sense. What are you going to do? And so you couldn't just sweep it under the rug. People needed to know, is this new thing that was discovered the 10th planet, or is it the death of the 9th planet? And everybody, I think, at this point knows the history of 5 years ago. 5 years ago, as this debate, the debate went on for 6 years. It started 6 years ago and went on for a year. Astronomers couldn't come to a conclusion. They finally brought it to the International Astronomical Union meeting in Prague, where they bickered and fought like babies for like 2 weeks. Was anyone there? Someone must have been there. Come on. Nobody in this crowd was actually there. I wasn't there either. So I was only watching it online and reading the newspaper articles. It was hilarious. Astronomers, scientists often fall prey to this, where they're in the middle of these vast arguments, thinking they're having the most important scientific argument of their times, when in fact it's really just the most important scientists arguing, which is really all it was. It's really just, and you could just tell that it's in many ways a lot of this is just matters of opinion. But everybody knows at this point what happened. Pluto got the boot. Actually, if you paid close attention, the vote was not about Pluto. Pluto was merely collateral damage. This guy got the boot, and Pluto had to go along with it. Actually, most people think of it the other way around, but that's the way I think of it. And they decided that there were 8 planets, and that everything else out there that's round is to be called dwarf planets, including Pluto and including this one. This is the stage in the talk where I often will sit and give you a 20-minute editorial on why this was the right thing to do. In some ways, I don't even feel like I have to. I feel like that showing this picture almost makes the point so obvious that it's no longer worth discussion. But it's the one point I would like to make, though, is that you still, if you're an astronomer and you sit down on an airplane, the first question anyone asks you, even if they don't know that you're me, they ask you is, what did you guys do about Pluto? I'm sure that astronomers in this room have had that question asked of them before. Yes, I see yeses. And astronomers will often answer something like this. They'll say, it doesn't actually matter. It's all semantics. And then they'll spend the 5 hours from here to the mainland telling you why their idea is right and everybody else is wrong. So do you guys have 5 hours? What do you think? So let me tell you. I'm going to tell you something slightly different. I'm going to tell you that it's semantics, and it matters a lot. It's not that it's semantics that doesn't matter. Yes, it's semantics, but the semantics matter, and here's why. The semantics, the descriptions that we give to the solar system, are our most basic way of describing our neighborhood, our universe around us, our planetary system. Most people in their lifetimes will not really learn the details, that there are asteroids here, that there are Kuiper Belt objects out here. But most people, in educated people, will learn about the planets. They'll learn that there's a sun and there are planets. And if we want to at least have them have the most correct idea of how the solar system is really arranged, we should tell them that there's a sun and then there are 8 big things that dominate the solar system. And then, if they're still interested, we can tell them, oh, by the way, those 8 big things are divided into rocky things that are smaller and gaseous things that are bigger. And if they're still interested, awesome. We can say, oh, and by the way, there are a bunch of asteroids between the rocks and the gas. And if they're still interested, we can say, and there's all these cool new bodies made out of ice on the outside. But that's many, many steps down. But the basic idea that there are 8 dominant objects that are pushing around everything else in the solar system is such an profoundly important description of the solar system that it's really important that our one word, we get one shot at describing the solar system for most people, and that shot is planet. And if we blow it with that one shot and do silly things, then we have become silly people, which is maybe not bad. But in this case, I do think it's bad. If we were to say that the competing proposal, and one that some people still won't give up, is that everything round in the solar system should be a planet. So I did a quick count the other day because I was curious how many round things are in the solar system. And the answer is something like 314. And 314, I say, that's kind of too big of a number for planets. And people say, oh, we can memorize 50 states. Why not 314 planets? But it's not really the point. The point is those 314 objects that are round are not a particularly profound set of objects. If you think of the solar system as 314 more or less equal objects, you have a really, really bad impression of what the real solar system is like. If you think of the solar system as 8 equal objects, it's not a great impression because you're lumping in Mercury and Jupiter, which are pretty different, but they behave the same way. They both have circular orbits. They dominate the region. It's not a bad description. If you go a few more steps, you can do even better. But this circular idea, which is kind of the, everything that you look at and should be a planet, you say it's a planet. It lacks any depth to it, and it's just not a very good educational system for explaining the planet. So it wasn't 5 hours that I talked to you about it, but I did at least do my 10-minute editorial. I will go on. So the object of finding these new things and these things bigger than Pluto was not actually to get astronomers to argue. That was just a side bonus. It was actually to get to do science. I started out looking for these things because I was looking for really good targets to come to Keck and look at with. And so I was really excited to have these things. I want to share with you a little bit of the science that we got to do from discovering these things. And I don't have as much time to talk about all of it, but there's some cool stuff. Here, I'm going to skip this part, but this is the typical picture you see of the solar system. And you see Pluto is about the same size as Mercury and not that much smaller than Pluto. If this were the real solar system, I would say Pluto's a planet too. This looks like it should be a planet because it's just about the same size as these things, and it would dominate. This is not the real solar system. This is only the solar system as seen on my daughter's placemat. So her placemat does not describe. She finds it very funny to tease me with it every day. She's like, "Daddy, look, it's Pluto. Daddy, look, it's Pluto." Anyway, so as soon as we find these things, the first thing we always do is try to come out to our very favorite telescopes. I say this every time I give this talk, even not when I'm here at my very favorite telescopes. There they are. And one of the very earliest observations that we got to do, a lot of you in the audience, I think you may have already heard talks. Well, actually, a lot of you are new, so I'll go through the detailed description about this one. But a lot of you know even a lot more than I do about this. But one of the very first things that we got to do about this with the discovery of this object. Oh, and I'm going to digress one more time and tell you this object, I've been calling it this object all along. We finally got to name it. Once it was declared to be not a planet, we were allowed to name it. We spent a lot of time looking for appropriate names, and we finally came up with one of the few Greek or Roman gods or goddesses that was left over, and I think it was waiting for us. And the name is Eris, E-R-I-S, and Eris is the Greek goddess of discord and strife. Every other Greek and Roman god or goddess had been used over the past 200 years when people discovered asteroids, because at first they called them all planets until they realized it didn't make sense. And they used all the good Greek and Roman names except for that one because they were saving it for me. I'm actually almost convinced that's true. Okay, so Eris, we immediately came out here to Keck to use, at that time, the brand new, fancy, no one else had one almost, laser guide star adaptive optics system. This thing is it's kind of the coolest thing in the world. Here's how it works. Some of you may have even, you can see like the laser movies on the web and stuff. So you take a laser beam, kind of like this one. You won't be able to see it Anybody see that? Yeah, it's kind of the way the laser works sometimes too. You take the laser beam, you shine it up in the sky. The laser beam goes up into the top of the atmosphere, and it reflects off of this tiny layer of material that basically is the remnants of little meteorites that have been deteriorated up in the top of the atmosphere. It goes to the top of the atmosphere, reflects back down, and you look at it in your telescope. So you're basically looking at a little spot of light that you put up there. But of course, that little spot of light goes to the Earth's atmosphere, and the Earth's atmosphere is all wiggly and woggly, and so that spot of light, that nice pristine laser spot, when it gets to you, it looks kind of wiggly and woggly like the atmosphere does. So you take that laser beam and you put it through a little camera, which then carefully analyzes it and puts it onto a little mirror, reflects the light down on this little mirror, and the mirror has little fingers on the back of it, which also go wiggly and woggly, except that they instead go woggly and wiggly and almost completely cancel out the atmosphere. And suddenly that really wiggly laser beam, which is going through here, suddenly looks like a nice little spot of light. And you've just spent a lot of money looking at a laser beam that you knew what it looked like to begin with. But if you're smart, you point your laser beam not to where you just want to look at a laser beam, but you point it to something in the sky that you want to also make as sharp as you possibly can and not be affected by all the wobbling of the light. And it's the coolest thing in the world to watch. You flip the little switch, and this big wobbly thing goes to a little point of light, usually, but not always. Because sometimes when you do that, it goes to a little point of light and a second little point of light right there next to it. And that second little point of light is the moon of Eris that was discovered. It was 5 years ago last week sometime, right here at Keck. And it was really super exciting. I cannot emphasize how exciting this was that we found out that this thing had a satellite to it. Having a satellite is good for a couple reasons. One is, everybody said, "Whoa, hey, it's got a satellite. It's got to be a planet if it has a satellite." And I just had to point out to people that of those things in the Kuiper Belt, something like a third of the objects in the Kuiper Belt also have satellites. They're pretty common. And of course, Mercury and Venus are planets. They don't have satellites, and they're planets, at least for now. So having a satellite doesn't do you any favors making you a planet, but it does let you do some very basic physics, which means you get to watch the satellite going around the object, and by how fast it's moving and how close it is, you get to do exactly what Newton did with the moon and its motion around, and you get to weigh the object. You get to see how much Eris weighs. And seeing how much Eris weighs was pretty exciting because you can do that very precisely. So we had observations from Keck. We had a couple of observations from Hubble Space Telescope. We put those together, and I was working with one of my grad students at the time, and she was convinced that when we finally figured out the mass of Eris, it was going to weigh less than Pluto. And the only reason she really thought that is because she thought it'd be pretty embarrassing for me, and she would find that enjoyable. So we made a bet. My bet was that it was going to be more massive. Hers was going to be less massive. We made the bet. We got those final data, and with this final orbit that we figured out, we realized that, in fact, Eris is about 25% more massive than Pluto, and the uncertainty there is only about 2%. So we still don't know exactly how big it is, but we know it's a good bit more massive than Pluto is. And that was a pretty exciting thing, and we'll come back to that in a very short minute because I need to go fast. Let me come back to that right now. This is the point where I should tell you about some of the most recent developments that have happened just even in the past year. In the past year, if you've been paying very close attention to this field in the outer solar system, you may have seen a headline in the science section of the New York Times back a couple months ago proclaiming that, in fact, Pluto is actually bigger than Eris. And the reason that Pluto might be bigger than Eris is because astronomers in Chile did this really fabulous experiment where they got it exactly the right time. They waited for Eris to pass in front of a star. And as Eris passes in front of a star, that star just blinks out, disappears. When it moves on, it blinks back in. And you can time that to incredible precision. So I had told you before that Pluto was 2,400 plus or minus 100 kilometers in diameter, and they came up with the fact that it's 23. My response was, woohoo, I did it right. So that sounds exactly right to me. Their response was, Pluto's bigger than Eris. And I said, what are you talking about? Pluto's 2376 kilometers. And they said, no, it's not. It's 2337. And I said, well, they say it's 2258. And I realized no one has a clue how big Pluto is. We now know very precisely how big Eris is, but nobody actually knows how big Pluto is. Pluto might be a little bigger. It might be a little smaller. The two of them are within, I think, 10 kilometers of being exactly the same size. Out of 2,400 kilometers, they're absurdly close to being the same size. And we won't know which one's really bigger until New Horizons flies by. And when the scientific paper describing this comes out, they will say, I think, Pluto is bigger than Eris, and that will be the accepted knowledge. And then when New Horizons flies by, the funniest possible outcome would be if the biggest discovery of New Horizons is that Pluto is actually smaller than Eris, which I would just find that amusing. But the very important thing, so imagine that now Pluto and Eris are the same size, or even that Eris is actually a little bit smaller than Pluto. Imagine this is true. The headlines you will read when this paper comes out in the next couple of months is that will say, I guarantee you, we should reconsider. Maybe Pluto should be a planet again. If it's not the smallest one, maybe it should be a planet. So I want you to evaluate this. I'm going to correct this slide. There's Eris. Now it's the right size. It did change. I really did. So what do you think? Does that suddenly change everything? I would say that changes pretty much nothing. So the argument might be, well, when we thought Eris was bigger, that forced the issue, and if we hadn't forced the issue, we may not have ever demoted Pluto. And that might be true, but it doesn't mean it was a bad thing. The solar system, as we describe it now, is a much more reasonable solar system. And even if Eris disappeared tomorrow, Pluto should still never go back to being a planet. It makes sense the way it is now, and I think it will stay that way as long as I'm alive. So let me just wrap up by showing you a few. I'm going to show you one more. I was about to say my favorite of my discoveries, but you're not allowed to do that when the others are in the room. So it's like children. You can't really say discovery. But this one was cool. How about that? Here's a discovery that we made back in 2002, and the object name was Sedna. I actually really enjoy naming these things. Sedna is the Inuit goddess of the sea. She lives in an ice cave under the Arctic Ocean. And we chose that name because this object was so far away that it was, at the time, the most distant thing that humans had ever seen in the solar system, therefore the coldest that we knew of in the solar system. Just like the discovery of Eris, which was a couple years later, we had the same question about Sedna. Does Sedna have a circular orbit, thus sort of planet-like, maybe it's really big and massive, or is it more like Eris? Eris is way out here now, but it goes back into the Kuiper Belt like a proper object should. So we didn't know. When we did the same trick that we did with Eris, went back in time, found its orbit. We don't know its orbit very well these days because remember that sort of 10% rule? We're not even close because its orbit looks like this. And it takes 12,000 years to go around the sun. So, give me another 120 years and I might be able to help you out some here. But we know pretty well. What we don't know is if it, where exactly it fits right out through here. It's a astounding object of a sort that astronomers never expected to find. These sorts of discoveries are to me even more exciting than things like finding Eris. Finding Eris, bigger than Pluto, all very exciting. We kind of thought there'd be something like that out there. Good to find. This, we had no idea. It shouldn't be there. This has rewritten a lot of the early history of the solar system of how we think it goes. We still don't know exactly why it's here, but we're working really hard to try to find out. But just as importantly, it shows you that there's this whole region. Here's the Kuiper Belt in here, where most of the objects are. There's this whole region out here that we thought was completely unpopulated that must be full of objects. Sedna certainly is not the only one out there. We are not so lucky as to find the only one. In fact, if you look at the orbit of Sedna, that 12,000-year orbit, the only time we could have discovered Sedna is in this 200-year period. Otherwise, it's too far away, it moves too slow, it's too faint. 200 years out of 12,000 years is 1 in 60. So we had a 1 in 60 chance of discovering it. And the obvious implication of that is that, not that we got lucky, but there are 60 of them that are the size of Sedna. And maybe we got a little bit lucky. Maybe there are only 30 of them and we got lucky. Or maybe we're a little unlucky and there are 120 of them and we only got to see one. The exact numbers don't matter very much. There's a huge population out there of these objects. Sedna is about half the size of Pluto. If there are 60 objects half the size of Pluto out there, well, even in the Kuiper Belt, there are only about 5 or 6 objects half the size of Pluto. Here there are 60. That's 10 times bigger population. If there's 60 that are half the size of Pluto, there are probably 30 that are the size of Pluto. There are probably 10 twice the size of Pluto. There's probably 2 or 3 that are 3 or 4 times the size of Pluto. The biggest object in this region out here may well be something like 4 times the size of Pluto, and that would put it at something like the size of Mars. The size of Mars, and I know this is the size of Mars because I cut and pasted Mars from here, so it's actually exactly the size of Mars. It leads to a really interesting question that I hope gets to be the next question that astronomers bicker and argue about, which is, what do you call it? Is this a planet? What do you guys think? Maybe? Yes? No? So, but let me tell you something else. Remember, it's not just that there's just this one object. The outer solar system doesn't look like this any more than it looked like only Pluto when only Pluto there. It probably looks about like this. What are those? There are thousands of these things out here. I think any system that doesn't recognize that these thousands of things out here are different from these 8 major things dominating the inner solar system is a pretty silly one. So I do think that these 8 ones will be dominant forever, but I think if and when we get to these discoveries of these really massive objects out there, it's going to be incredibly exciting. We're going to learn a lot about the physics and the chemistry of the outer solar system, and we're going to be discovering these worlds that are on the scale of things that we think about, of Mars, of the moon, and that's just going to be a tremendously exciting thing. And I think it will lead us to refine once again, which I think is okay, our ideas of what a planet is, what a planet should be. In the same way that these discoveries of things around other stars are expanding once again. I think in all cases we will come down to this idea that all planetary systems are going to be dominated by a small number of massive objects like our planetary system is. I might be wrong on this one. Someone might prove me wrong tomorrow. But I think it's probably true. I think these will all be planets, and I think the rest of it are a fascinating set of bodies to study forever, which is what I'm going to be doing, but I think they're not planets. When I find one of these things, the first thing I'm going to do is come back here to Keck to study it in gory detail. Second thing I do, I'll come back and tell you guys all about it. In the meantime, you can pay close attention. You can read my sort of sporadic blog, which I try to update as much as possible on what's going on out there. And when I have less time and I can't write quite as much, you can, of course, find me on Twitter right there. And my last job, of course, is that this was one of these nice artist renditions that was painted right after the discovery of Eris, which was at that time described as the 10th planet. And this was the portrait of all 10 planets. But this one's not, and I also have to get rid of that other pesky one there too. But now my work is done. I'd be happy to take a few questions, sign books later, and thank you very much for coming out tonight.